foundations of geometry is the study of geometries as axiomatic systems. There are several sets of axioms which give rise to Euclidean geometry or to non-Euclidean geometries. These are fundamental to the study and of historical importance. But there are a great many modern geometries that are not Euclidean which can be studied from this viewpoint. The term axiomatic geometry can be applied to any geometry that is developed from an axiom system, but is often used to mean Euclidean geometry studied from this point of view. The completeness and independence of general axiomatic systems are important mathematical considerations, but there are also issues to do with the teaching of geometry which come into play. Axiomatic systems, based on ancient Greek methods. An axiomatic system is a formal description of a way to establish the mathematical truth that flows from a fixed set of assumptions, although applicable to any area of mathematics. Geometry is the branch of elementary mathematics in which this method has most extensively been successfully applied. There are several components of an axiomatic system. Primitives are the most basic ideas. Typically, they include objects and relationships. In geometry, the objects of things like points, lines and planes, while a fundamental relationship is that of incidence, of one object meeting or joining with another. The terms themselves are undefined. Hilbert once remarked that instead of points, lines and planes one might just as well talk of tables, chairs and beer mugs. His point being that the primitive terms are just empty shells, placeholders if you will, and have no intrinsic properties. Axioms are statements about these primitives. For example, any 2 points are together incident with just one line. Axioms are assumed true, and not proven. They are the building blocks of geometric concepts, since they specify the properties that the primitives have. The laws of logic, the theorems or the logical consequences of the axioms, that is, the statements that can be obtained from the axioms by using the laws of deductive logic. An interpretation of an axiomatic system is some particular way of giving concrete meaning to the primitives of that system. If this association of meanings makes the axioms of the system true statements, then the interpretation is called a model of the system. In a model, all the theorems of the system are automatically true statements. Properties of axiomatic systems. In discussing axiomatic systems, several properties are often focused on. The axioms of an axiomatic system are said to be consistent if no logical contradiction can be derived from them. Except in the simplest systems, consistency is a difficult property to establish in an axiomatic system. On the other hand, if a model exists for the axiomatic system, then any contradiction derivable in the system is also derivable in the model, and the axiomatic system is as consistent as any system in which the model belongs. This property is referred to as relative consistency or model consistency. An axiom is called independent if it cannot be proved or disproved from the other axioms of the axiomatic system. An axiomatic system is said to be independent if each of its axioms is independent. If a true statement is a logical consequence of an axiomatic system, then it will be a true statement in every model of that system. To prove that an axiom is independent of the remaining axioms of the system, it is sufficient to find 2 models of the remaining axioms, for which the axiom is a true statement in one and a false statement in the other. Independence is not always a desirable property from a pedagogical viewpoint. An axiomatic system is called complete if every statement expressible in the terms of the system is either provable or has a provable negation. Another way to state this is that no independent statement can be added to a complete axiomatic system which is consistent with axioms of that system. An axiomatic system is categorical if any 2 models of the system are isomorphic. A categorical system is necessarily complete, but completeness does not imply categoricity. In some situations, categoricity is not a desirable property, since categorical axiomatic systems cannot be generalized. For instance, the value of the axiomatic system for group theory is that it is not categorical. So proving a result in group theory means that the result is valid in all the different models for group theory, and one doesn't have to reprove the result in each of the non-isomorphic models.